let's talk about velocity. So let's say you're driving down the road in your nice car, and you start to think to yourself, how fast am I going right now? Well, we all know how to calculate speed, or velocity. It's just displacement over time. Displacement is just a fancy word physicists use for distance or direction.
When we graph displacement as a function of time, we can see that velocity is the slope of the line. For example, if you travelled 100 metres in 50 seconds, the slope of the line would be 100 divided by 50, so your velocity would be 2 metres a second.
This is the same way that average speed cameras work. First, they detect your car's number plate at the time you pass a certain point. Further down the road, they detect the number plate again. Using the previous formula, the speed camera assumes your average speed. However, this assumes you drove the exact same speed the whole distance. This raises ethical issues, as average speed cameras do not measure the instantaneous velocity, but instead calculate the minimum time the distance could be travelled at the correct speed limit.
However, in the real world, we do not travel at constant velocity. We know that a real speed curve would look a lot more like this. In some areas, you are travelling much faster than the average of 2 metres a second, and in some sections, much slower. If we wanted to find the speed at this point, for example, we could take smaller and smaller averages to try and calculate an instantaneous velocity.
What we really want is displacement over time when time equals 0. But we all know you can't divide by 0. Another way to think about this is that you want an infinitely small change in d over an infinitely small change in t. This is what's known as the rate of change.
People have been working on calculating rates of change for centuries. Ancient Greek mathematicians such as Archimedes and Democritus first laid down the framework for this field of mathematics. The field was formalised in the 17th century by Isaac Newton and Gottfried Leibniz. This was the birth of calculus.
Newton and Leibniz were able to solve the problem of dividing by 0 by imagining that a line is composed of an infinite amount of infinitely small points. This approach is known as infinitesimal calculus.
An infinitesimal is normally described as a number that's bigger than 0 but smaller than all other real numbers. Some people explain this by saying that it's 1 over infinity.
The use of infinitesimals introduces a margin of error into their calculations. Despite this, Newton and many other scientists and mathematicians have been able to use this model to make accurate predictions about the world, such as the effect of gravity between the Moon and the Earth, and therefore the orbit of the Moon. This tiny assumption is also made by your eyes when viewing movies. Think about film reels. They are actually a long series of images shown very quickly. Similarly, an audio file is broken up into many small segments. Despite this, your brain is tricked into thinking that they are a continuous stream of sound and video, just as the infinitesimal approach to calculus assumes that a curve is non-continuous but can still be used in accurate mathematical models. Conventional speed cameras detect the speed of a vehicle as it passes a point. Using radar or electrical sensors, it then detects the speed as the car reaches another point, very close to the first. This is similar to the math behind infinitesimals. The speed is calculated by approximating the exact distance by measuring the gradient between 2 points very, very close together. As you can probably guess, there is another ethical issue to consider with conventional speed cameras. Drivers can slow down for a small portion of time to avoid being fined by a speed camera and then continue on speeding.
Despite these applications, the nagging margin of error introduced by infinitesimals remained. This problem was solved in the early 19th century by the French mathematician Augustin Louis Cauchy, who was able to replace infinitesimals with the concept of the limit. A limit, as you may know, is what happens to a function as it approaches an asymptote of a discontinuous point. In other words, what we want to calculate, the speed when no time has passed. We know the slope m is equal to the change in y over the change of x. We can rewrite y as a function of x, with y2 being a function of the change in x. Using Cauchy's definition of a limit, we can think of the slope as being equal to y2 as a function of the change of x, minus y1 as a function of x, divided by the change in x as the change in x approaches 0. This is the definition of the derivative. When thinking about velocity, we can simplify this to the change in d over the change in t as the change in t approaches 0.
Through the application of this definition of the derivative, we can model a broad range of concepts. This allows us to solve problems from the calculation of drug dosages to aviation engineering and even space exploration.
The speedometer in your car measures instantaneous velocity, as you may have noticed when driving. The needle on your speedometer changes to show your speed at any given moment. Instantaneous velocity of the car is calculated using electromagnetism or electric currents. The speedometer reading appears to be a limit of the average speed as the time interval gets smaller and smaller. This is the idea behind the derivative. This example gives a physical interpretation of the derivative. If we graph this definition of the derivative, we get the tangent line at any point that we choose on the curve. Therefore, the slope of this line gives us the instantaneous velocity at any point.
This makes sense, because when the car is not moving, the slope is 0, which means that your displacement isn't changing whilst time is changing, which of course makes sense because you're not moving. If we go to the other extreme of this and make the line vertical, it would mean that you're moving in space but not through time. The slope of this line is infinite, meaning you would have infinite velocity, and we all know that's impossible, unless you're a photon. But that's a video for another time.